Okay, so I think we can start. So, so it's a great pleasure for me to introduce our speaker today. It's Dmitro Перекресенко from HDI Zurich, and he's going to talk about constructive universal high-dimensional generation through network. So please. So usually our talks, so usually it's for 1 hour, but it's up to you. So if you can finish earlier or maybe additional like 10 minutes, so it's okay.
Perfect. So, yeah, I can start.
Yes, please.
Okay, good. Perfect. So, hello everyone. Good evening. I want to present my recent work. It's about approximation probabilities of generative networks, and in particular, what we're gonna do today. Our goal is to find a construction that transforms uniform, one-dimensional uniform distribution through a neural network into an arbitrary high-dimensional arbitrary distribution, not necessarily uniform. And this is work that I did together with Stefan Müller, Leandro Eberhard, and Helmut Bolzke. Okay, so a bit of motivation. Why is it important to study approximation probabilities of generative networks, and especially increasing of dimensionality, is that they actually widely used for generating images, natural language, audio, and so on. And even in practice, it happens for like in some architectures, like variational autoencoder, Wasserstein autoencoders, that there is some kind of noise distribution, low-dimensional noise distribution in the input, and then at the output, you generate a high-dimensional data distribution, which is different from uniform or normal distribution. And what we try to answer in this talk is that there exists a fundamental limitation going from low-dimensional to a higher-dimensional distribution. I will talk about feed-forward neural networks, so they are depicted on this image. They typically, so they have input layer, hidden layers, and output layer, and the connections are only between neighboring layers. And mathematically, the neural network can be described as the composition of affine maps and nonlinearities. So here we have a definition. What we should pay attention to is that, affine map is basically like multiplying by matrix, saying simply, and nonlinearity function would be ReLU, which is which we act component-wise. So we apply it for every element of the incoming vector, and we define 3 functions. First is network connectivity, which is the total number of non-zero parameters in the affine maps. It's basically number of parameters in the network. Second is depth, is L of f here. So so L of f, which is a number of these affine maps, and the width of the network is the maximum size of the maximum dimension of the affine map. Basically maximum number of neurons in each of the layers, to say simply. And we denote by, sorry. So, and we denote by n d small, a subscript d prime set of ReLU networks with input dimension d and output dimension d prime. In this talk, we typically have input dimension 1 because we're transforming one-dimensional uniform distribution, and output dimension d, which because we want to approximate arbitrary high-dimensional distribution. So this is short outline. So in this talk, I want to give 2 main ideas. First is I would like to talk about Sotos function and its central role in the ReLU network theory. I will tell you that, I'll talk about approximation of x squared and polynomials, why this proof is based on Sotos function. Then I will talk about periodic function and how some properties of Sotos function is very nicely fits with approximation of periodic functions. Then I will talk about another nice property of the Sotos function that is actually a very nice, I will show you a very nice construction that allows us to transport between uniform distributions of different dimensions. And after like this introduction about Sotos function, I will actually talk about transporting between one-dimensional uniform distribution and arbitrary high-dimensional. Oh wait, this shouldn't be uniform. Sorry, arbitrary actually high-dimensional distributions, so no uniform. And then I first start with two-dimensional case because it's very easy to understand the two-dimensional case. And I will talk about generalization to d dimensions, which is problematic to understand, it without diving deeply. But I will outline how to extend the construction to d dimensions. So first, I'd like to talk about Sotos function. What, like I said, is a central piece of the ReLU network approximation theory, and so what is it? It's defined as follows, and its plot can be seen on the left bottom side. So here, it's just a triangular function with a support between 0 and 1. So its peak is right in the middle in points 1/2. And what is nice about this function is that when you compose it with itself, the number of these triangles, or they can call them t's, every time doubles. So every time, so on the left side, we have a pure Sotos function of order 1, is just a triangular. But if we compose it with itself, then a number of t's doubles, basically becomes 2. And then when we apply it 3 times, compose it 3 times, the number of t's becomes 4. So we see that the number of t's in the Sotos function grows as 2 to the power of s minus 1. It's a number of okay. First, why this? What is nice about this function from the neural network point of view is first, it can be easily realized as in a ReLU network, because just like a composition, it's just linear combination of 3 ReLU terms. It's in the bottom. So basically, you can say that it can be represented as a 2-layer ReLU network, of which 3. And what is nice about Sotos function from approximation theory perspective is that the ReLU networks always generate piecewise linear functions. And usually, in order to approximate something complex, number of linear pieces in the ReLU network should be quite large. What is nice about Sotos function is that it is relatively cheap. Using Sotos function, it's relatively cheap to obtain a lot of linear regions, because you see that every of the tools, it contains 2 linear regions. And since we see that every time we compose a Sotos function with itself, we double the number of linear regions, but for this we pay the price of increasing the depth of the network just by 1, because every time we compose, so basically if function g1 requires depth 2 network, then G2 will require depth 3, and so on. So we're paying, by adding 3 additional neurons and 1 layer, we're doubling the number of linear regions. So that's first hint why Sotos function is quite interesting from the approximation theory point of view. And the first result that is based on the Sotos function is actually x-square approximation. if we so we will let's us approximate the x square with 2 to the power of m plus 1 uniformly spaced nodes. So basically, we are making a piecewise linear approximation of the quadratic function, and the breakpoints are distributed uniformly on the 0-1 interval. So if we do such a piecewise linear approximation, then the approximation error scales exponentially with m, this number with a degree of this interpolation. So it would be nice if we want to approximate square function, it would be nice if you can construct using neural networks this function f of m. And that's exactly what we can do using a Sotos function that is the result due to Dmitry Avotsky. So you can see that on the right-hand side, there is this dashed line, which is a parabola. So like x square, the plot of x square, and each of the f0, f1, f2, it's first order interpolation, second order, and so on. And if you and on the left hand side, you see the Sotos function. So let's now look at the just to understand the idea of why Sotos functions are helpful here. Let us look at the function x, f of x equal to x, so just a diagonal, and see what happens if we subtract the order 1 Sotos function, which is just a triangle. That would be exactly this this line in red. So we see that it actually touches the parabola in 0.1/2, exactly like where the maximum of order 1 Sotos function is. And then if we now look at the next linear piece, so now we're taking linear piece of the f1, basically we look at f1, and we consider the piece from 0 to 1/2, we again see that the green line, it's an approximation, it's a cursor approximation of x square, and it actually it's obtainable by subtracting from the red line another scaled Sotos function. So here, and if we and the maximum is exactly in 1/4. So that's actually where the point of interpolation is. So if we continue this way, it will be looking like kind of a fractal, but the basic idea is that we can obtain this interpolation of x square, the next order interpolation, by subtracting a scaled version of order m Sotos function. And this iterative equation leads to overall representation of this sort. So we found out that we can like approximation to x square that is exponentially improving with m is representable by just x minus sum of the scaled Sotos functions of different order. And since we know that each of the Sotos function can be realized by a ReLU network, then it's quite straightforward to show that a combination of ReLU networks is also a ReLU network. So in this way, by proving this relation, approximation relation, we can prove that x square is approximable by a ReLU network with with infinite accuracy. So why, and now x square result is quite important, and we will show that it was actually based on the Sotos construction. And what follow up is that approximating x square opens us universal approximation result. Since if we approximated x square, then we can actually approximate a multiplication, because it's just a linear combination of square terms, and each of them separately we can approximate with a ReLU network. And approximation of multiplication in line allows us to state a polynomial approximation theorem, and then by Weierstrass theorem, which says that polynomials are dense in the space of continuous functions, that shows just that ReLU network can approximate any continuous function, which is nice. And everything was based on the Sotos function. So that's the first nice result that's based on Sotos function. The second one is related to the periodicity of the Sotos function. And since you saw that the Sotos is basically a sequence of t's that are just identical, we can use that to extend, to actually improve approximation of periodic functions. So let's say we have a periodic function, let's say cosine. Of course, we can say that cosine is a continuous, and then we can just do a polynomial approximation for the cosine on any interval we want. However, we would face a very high Taylor coefficients, and obvious, like the larger the interval we approximate, on which we approximate the cosine, the more complexity the polynomial, Taylor polynomial should be. And in a way, it's detrimental to approximation if we, instead of periodically extending the one period of cosine, we will be approximating a whole, like all 5 periods by, let's say 5 or any periods, by just straightforward polynomial approximation. So that's the idea. Idea is that we can approximate one period of the periodic function, and then with the Sotos function we can extend we can extend this one period to as many periods as we want, and we do it quite efficiently because Sotos function is constructed very efficiently using in terms of parameters of network. Okay, so that was an introduction, and we actually have a cosine approximation theorem. It says that cosine can be approximated, and if you compare it with the previous one, the complexity of the network is lower. And what is the idea? First idea is straightforward. We just construct one period of cosine using Taylor approximation. So we reuse the result from the previous slide on a polynomial approximation. Then, since we can find with Taylor approximation, we can find such a polynomial that approximates it up to accuracy epsilon divided by 2. And then in turn, we can approximate polynomial with accuracy epsilon divided by 2. And in total, we obtain that the one period of cosine is approximated with accuracy epsilon. Okay. Now the Sotos trick comes into play. So what we claim, and it's actually true, is that so what we claim is actually true, that you can extend cosine instead of using these large parameters like 2 to the power of s. You can actually use a Sotos function of order s, and you can see it on this on the image on the right. So what happens if in cosine, instead of using x as an argument, we're using g of x? So basically we're using this function top, on the left, in the image on the left side, the middle on the left side is one period of cosine, and in the image on the left, bottom left image is a function that is obtained by changing the argument from x to g of x. So what happens? If we take the g of x as an argument instead of x, we see that the argument changes from 0 to 1 on the interval from 0 to 1/2. And then it goes back. So the argument decreases from 1 to 0 on the interval from 1/2 to 1. And how does it relate to the plot? So what it happens is that first on the interval from 0 to 1/2, we actually speed it up. So this function is actually 2x. So we plotted this one period instead of on the interval from one period of cosine instead of interval 0 to 1. We squeezed it to interval 0 to 1/2. And then, so basically you can look at it as we traveled along this period from 0 to 1, but on the bottom plot, it corresponds to traveling from 0 to 1/2. So here, what happened next is we actually changed the argument from 1 to 0. And this corresponds to going back in this on the period from 1 back to 0. So, and since the function is even and one periodic, this corresponds in down that we just plotting exactly same mirror image of the period. And obviously this extends to higher order of Sotos. So if you have Sotos of order 2, which you have 2 t's, that means that the function will change from 0 to 1 and back 4 times. So it's first 0 to 1, then 1 to 0, then again 0 to 1 and back. And this corresponds to 4 periods because we moved over the whole domain 0, 1 4 times. And in this way, we are getting rid of this problem of high magnitude of parameters. In this case is 2 to the power of s, which exponentially increasing, by replacing it with Sotos function, which traded off this high magnitude of parameters with linear increase in depth. So this is just to say, just to extend, how would you approximate cosine ax, where a is arbitrary value, and this network doesn't have this network because we replaced this high magnitude parameters with Sotos function. It doesn't contain have this very high magnitude parameters. And this idea of periodic extension leads us to the third important property of the Sotos, which is used for now in generative networks. It can actually be what's nice about Sotos function is that if we increase number of periods, then the Sotos function represents a space-filling curve. What is space-filling curve? So even graphically, it's it could possible to explain it in that way that since we know that every pure Sotos function is just one triangle, but if we have we increase the parameter s, which is the order of Sotos linearly, it exponentially increases a number of t's, and then at some point the t's become so dense that like in the limit, it actually covers two-dimensional square instead of like basically it took a curve and covered with this one-dimensional curve a two-dimensional square. That's the idea of space-filling curve, that we found a curve that fills the space, like covers the two-dimensional like square with one-dimensional curve. Okay, and the important result relating to that is the following, due to Bailey and Telgarsky, that there exists a ReLU network of a certain connectivity, which is number of non-zero weights and depth, such that Wasserstein-distance between networks push forward one-dimensional uniform distribution and multi-dimensional uniform distribution is scaling, decreasing, is error increasing exponentially with with depth, basically. And the main proof idea of this is first we have to remind ourselves what is Wasserstein-distance. For simplify things, Wasserstein-distance is also called Earth mover distance, that you basically you have to, like in the beginning, you have a certain probability mass, which you can visualize it as a sand of like 1 kilo of sand, and it was on the interval from 0 to 1, one-dimensional interval. And then the idea is, let's say about 2-dimension, is that the idea is some like of Wasserstein distance is how much work one has to do in order to move this 1 kilo of sand in order for this unit square in 2-dimension be filled uniformly. So you, like every small area of the square should have a weight of sand proportional to the area of that region. Okay, and so that's like, and this sand is a probability mass. So what happens in this case, like with a space filling property, let's look at the image below. If we take a plot of the Sotos function and split it into columns such that every column contained one linear region, then, and you divide this by small horizontal lines, you obtain boxes where each box has equal amount of sand, or like length of this curve that is inside this inside of each of the box. And so you see that like, yeah, each box, if they have equal size, they have the same amount of same length of the space filling curve, you can say. And then if this is true, then we know that the network Sotos function, so this G of S, it has s to the power of s minus 1 t's, and that means that every linear piece, which is a half of 1 tooth, is of size 2 to the power of minus s. And then if you look at the problem that you have like a small box of size 2 to the power of minus s, and you have to compute the work, like Wasserstein distance between like some mass centered like somewhere in this box, and to distribute it between some mass and distributing it uniformly, you will find that the work cannot be more then the mass, probability mass concentrated here multiplied by square of 2 divided by 2 power of s. Oh, actually, so here it's, sorry, that was wrong because it should be square root of d, depends on dimension. In case of 2, there is the maximum distance between the points is square root of 2 divided by length of the square, the side of the square. Okay, so and in this way, by delivering the right mass, uniform mass to each of these small boxes, we can show that the Wasserstein-distance between distribution we obtained by pushing forward uniform distribution, one-dimensional uniform distribution, and the space-filling curve, and the high-dimensional distribution is decreasing with the size of the small box, and with the size of the small box, and the construction Bailey and Telgarsky had was based on Sotos function. So the map looks like this. So X is a uniform distribution. It was mapped to this d-dimensional construction. And here in the plot below, you can see the visualization of the construction for 3 dimensions. And so if you take a projections on any of the sides, this is for G, like third order Sotos function, means like it has 4 t's. So we take any projection on the sides or from the top, you will see this 4 t's, because it's you see that every dimension you have to double the order of the Sotos function, because on each of the linear pieces there has to be basically, if you define it as a, so your base distribution is S, so this S order S Sotos function should lie on each of the linear pieces of the Sotos function of the. So basically, as this 4 t's standing on one of the linear pieces of the underlying Sotos function. So if you project it on 2 dimensions. And in this way, by increasing number of t's or a parameter s, you can fill the whole 3-dimensional ball or d-dimensional, doesn't matter. Okay, so we covered the properties of Sotos function and how it can approximate uniform distributions. So now we are ready to go to arbitrary distributions, and then I will show you construction for 2 dimensions. And for high dimension, it's more complicated, but I'll outline how to do it. So but our goal is to transport uniform distribution to arbitrary high-dimensional distribution. And in order to do that, we have to define a special class of distribution, which is called histogram distributions. Why they're special? So on this plot, you can see on left side 1-dimensional histogram distribution, on the right side 2-dimensional histogram distribution. And what are they basically is they are piecewise uniform distribution, you can call them. So basically there is a parameter n, which splits the domain in every dimension into n parts. So it splits here, you have 1 dimension n equal 5. So it splits the domain into 5 pieces, each of length 0.2, and then here actually what is shown is PDF of the distribution. So and every so distribution has probability here, has some fixed probability to land into area 0 to from 0 to 0 2, but inside that region between 0 and 0 2, the distribution is uniform. So that's why it's called piecewise uniform or histogram. And in this 2 dimensions, you see that you basically split the square into this n by n table, or like histogram, and each of these boxes, on each of the boxes, the distribution is uniform, but the distribution on the box by itself can be different from distribution in the other boxes. And why this such distributions are, I will show next, like why these distributions are important for neural networks in particular. So if we transport, so our goal would be to transport uniform distributions through the neural network to the histogram distribution, so this part in the middle. And then by controlling the histogram parameter n, we can approximate any arbitrary distribution. So that's our goal. And for illustration purposes, I will right now do for d equal 2. Why the histogram distributions are special? So we know that in order to obtain an arbitrary distribution in one dimension, we can take an inverse CDF of the target distribution and push uniform one-dimensional uniform distributions through that inverse CDF. So you can see this image that like if you construct a curve, which so basically here you see that this line is I don't know, approximately 0.125. So on the, and we know that this, so we know that this, the probability mass of 1/8 was mapped. So the mass of 1/8 was mapped to the interval from 0, like from 0 to 0.25. So the probability of after like of landing, for the point of landing into interval from 0 to 0.25 is 1/8 after this transformation. And then if we, so basically if the angle is higher, the higher the angle, the in this inverse CDF, not higher, the lower the value of the angle, basically, then the more of a distribution lands into the interval. So we see here an interval, it's more, the angle is less than in the previous one. So distribution will land more distribution here. And this is even steeper angle than we get a maximum distribution in this side, because we transmitted maximum probability mass to the interval between 0.5 and 0.75. So that's the idea, and it works for any like arbitrary one-dimensional distribution. We just need to you need to find inverse CDF and push through a uniform distribution, and then you obtain the distribution. What's special about histogram distribution is that for ReLU networks, always generate piecewise linear functions. Therefore, if you push through uniform distribution through ReLU network, you will always obtain histogram distribution. And there is, and this works another way around. So if you have a histogram distribution, since ReLUnet can implement any piecewise linear function, you can find a piecewise linear function that generates such histogram distribution. And now, like if we return back to the Bailey and Telgarsky, yes.
Sorry, may I ask you a question? So
yeah, of course.
on the previous slide.
Yes.
And so if your one-dimensional distribution has smooth function, not like piece-like.
Yes.
Like piece function, but smooth. What's
then
happening in this case?
In this case, you will not get a histogram distribution. You will get like
yes, for sure. Yes.
Yes.
But it's not a problem. or it's a problem?
It's not. So like the point here is that we are considering ReLU networks, and ReLU networks always produce piecewise linear functions. So there is no, we cannot obtain smooth inverse CDF via ReLU networks. So it can, they basically, if you push through this like uniform distribution through ReLU network, you will always obtain histogram distribution. You cannot obtain anything smooth or yeah.
Yes, for instance, normal distribution you cannot get in this way.
Yes. Yes.
Okay, thank you.
Yeah. Good. Good. So you can obtain just history. It will look like a step function. The PDF of the distribution will look like a step function for inverse CDF produced by ReLU networks, and uniform distribution pushed through them. Okay. And now if we go back to the result of Bailey and Telgarsky, we can actually answer why the distribution they generated using their construction was uniform. That's the reason, because PDF of the uniform distribution is actually just X. So inverse CDF of uniform distribution is just this diagonal. And since they propagated, they basically copied via Sotos function this inverse CDF corresponding to uniform distribution, they obtained a space-filling curve corresponding to uniform distribution. So that's how they generated like uniform distribution because they propagated inverse CDF of uniform distribution. What we do, we will take another piecewise linear CDF and propagate it through the ReLU function. So what ReLU function does, we remember from the cosine approximation, that it actually copies the function we give it as an argument to. So in this case, we have such function here, which is not a bit complicated. So like it has some pieces, like a lot of linear pieces. And if we take this inverse CDF and take, let's say, G2x as an argument, we'll obtain the copies of the inverse CDF of some arbitrary, like some distribution of a new distribution. And then if we do the same kind of proof, like again, like splitting them into columns where each column corresponds to one half of the tooth in the Sotos function, and then do again here like this, we will see that the distribution we generated is actually not a uniform anymore, but a distribution according to the inverse CDF we propagated through Sotos function. So let's see on the next slide. If we consider such a map in 2 dimensions, then and we propagate the function on the left side, we'll obtain the copies of it. And you see it already that, let's say in this part, the number, like the length of the curve, let's say, it's is much less than what let's say this part has, because there is like, oh no, not this part. Okay, it's not aligned, but okay, the angle, where the angle is high, so here should be like a lot of probability mass concentrated. So basically, if you propagate such inverse CDF as on the left side, you will obtain histogram distribution stretched over the square. So if you project, so basically this curve like is corresponding to inverse CDF of one of the columns. So it was just like 0.5, 2, 1, 0.5. So it was something like some distribution like this. So this is inverse CDF of the histogram distribution of this sort. And what we did by generating this space-filling curve, we obtained a approximation to the histogram distribution. And the proof works in exactly the same way as it was for in Telgarsky. You just split into boxes and prove that every box has weight according to the distribution, histogram distribution. And this can be extended in the obvious way. Since we want, so before we saw that there was no variability in the columns. So basically every row had the same, row had the same probability. Like there was no differentiation between the columns. Every column is the same. But now, let's say we just take those distributions we generated and make several number of them. So we generate space-filling curve for the first, this column of the histogram distribution, second, third, and so on. They can be different, but then we just generate them and stitch them together. And we will obtain space-filling curve looking like that, like in the middle. And such space-filling curve would generate a distribution on the right, which has variability in the columns. And the map would look like on the top. So here we also have a marginal distribution, which is basically identifies the probability of each of the columns. And then we are taking mass that is given us by this marginal distribution and distribute the mass with the Sotos function according to the f of I, where f of I is the inverse CDF of the i's column in this two-dimensional histogram distribution. And in this way, we can approximate any two-dimensional histogram distribution by just taking each of CDFs of each of the columns. So there will be, in this case, 4 of them, and one inverse CDF of the marginal distribution. So in total, we need like 5 parameters, 5 inverse CDF to and the Sotos function to actually approximate such distribution. And this can be extended. And this is, maybe I don't go deep into that, but it's possible to generalize it. And the idea is in a way similar. You have to look, like in the way we looked at the marginal distribution in the previous slide, that we took we took only the mass that corresponds to the column, and we used only it to propagate it with the Sotos and generate space-filling curve. It happens the same in higher dimensions, but yeah, maybe not go deep into that. Basically, here I explained like what those functions does, and then there is a special z function, and the map is just d of such z functions, and we obtain that arbitrary histogram distribution of dimension d and precision m can be generated with this map, and the error will approximate with this map, and the error will decrease as square root of d divided by n multiplied by 2 to the power of s. So it decreases exponentially in s, where s is this parameter of the Sotos function, which is nice because increasing the depths through the Sotos function is cheap, as I said before. It's only adding 1 layer and 3 additional parameters. in general, we can formulate the following theorem that if there is a histogram distribution of dimension d and precision n, then there exists a ReLU network with the connectivity, so number of non-zero elements scaling as n to the power of d. And the second term, which is not so important because s, I think it's less than n usually, but it's like important to say it here. And the depth scaling as s multiplied by d, such that we obtain this exponential approximation accuracy in s. Yeah. So, and what is nice about this result is that the number of parameters in the histogram distribution is n to the power of d minus 1. So if you remember, like, let's say two-dimensional distribution, you know that every box has a certain probability assigned to it, but they all sum up to 1. Therefore, in this case, you need to know 8 values of probability distribution of 8 boxes, and then the 9th you already know. So, and this generalized to higher dimensions. So the number of parameters, now, like to identify arbitrary histogram distribution is n to the power of d minus 1. And what we found is that our network has also same order of parameters in it. That shows that it's likely to be optimal for that. And the special case, as I told you, when all CDFs are just x, f of x equal to x, it means like a uniform. In that case, n equal to 1. So there's like precision of the histogram is just 1 because there is only one box, and it becomes a Bailey and Telgarsky result. And this is like an extension that actually for Wasserstein-distance, it's true that if probability measure is concentrate, is basically supported on 0, 1 on the d-dimensional block cube 0, 1, and then you can find histogram distribution of resolution n such that the error will decrease linearly with n with the histogram resolution. And finally, so that's the final slide, that you're combining those two results, like approximation for the histogram with approximation of arbitrary distribution by a histogram, and you can find that there exists a ReLU network with that many parameters, the depths, such that the Wasserstein distance between the arbitrary distribution supported on 0, 1 and the push forward uniform through our network is bounded by these two terms. And the one term is a decreasing exponentially with depth, which is nice, this one, and it's negligible compared to the second one. And in this way, we can make some kind of conclusion that so first term is coming from the dimensionality increase and approximating of histogram distribution, but second term is approximating of arbitrary distribution via histogram. So, and we see that approximation via histogram distribution is that term is much more influential than the first one. And in that case, we can say that our method is like basically has the same complexity as the histogram approximation method when you go from basically d dimensions to d dimensions. And our method is going from basically one dimension to d dimensions. And we actually obtained same asymptotics. That's why we say that real networks have no fundamental limitation going from low dimension to a high one because the first term is negligible compared to the second. Yeah, thank you for your attention. If you have any questions, I would be happy to answer them. So this talk was based on the like 2 papers listed here.
Okay, Dmitry, thank you very much. So, dear colleagues, do you have questions?
So one question. So thank you very much for very interesting talk. But I just wonder, in the title of your talk, you say about high dimensional distribution. Yes, but in the results, you have square root of d divided by n. This is one part, and also you have number of parameters, n to power d. So if dimension is, say, 100, and this is not high dimensional case, so you have just huge numbers. Number of parameters, n to power d.
Yes. I agree. Yes.
Or maybe it's better to say in your title low dimensional case.
Okay. Yeah. We're just providing a method to generate high dimensional distribution. We estimate number of parameters required for that. Yes, it's not feasible to like construct it for high dimensions, but I mean, it's not yeah, you have a high values of connectivity will be really high, but it still works like in a way, like you have resources, you can implement it. It's not limited to low dimensions in that way. It's like, yeah, parameters are high, but the method works. So, and it's theoretical anyway, because like.
Yes, theoretically everything is fine, but when you try to realize it, maybe you will have problems. But another remark is the following. So, as I understand, it was not necessary to explain what you've done in terms of neural network. In fact, this is just some analytical transformation you use. That's all. So maybe neural network just help to make some kind of visualization of your arguments. But in fact, it's not necessary.
I agree that like neural networks is not necessary, but what is important here is that neural networks can implement, I mean, in theory, it's possible to find such parameters that transport like one-dimensional uniform to a higher dimensional arbitrary distribution through this construction. So it's more, yeah, I agree that it's not that like only neural network do it. It's more saying that we can find a way how neural network can do it. And though, because it's not so straightforward how to increase dimensionality, like in practical.
Dmitry, I mean just it was not necessary to use the language or terms of networks.
Okay.
Just some kind of composition of some functions and so on.
That's a tricky question because like when we work with this neural network approximation theory, we try to show what is theoretically possible with neural networks. So the idea is to study neural networks, and if we say that okay, it's not a part of neural networks, then it makes it outside of like the scope of, like actually the extension of this work. What we like actually have a paper on this, when it will be published, is we actually quantize a network and develop theoretical estimates on how many bits one needs for the neural network to encode certain distribution. And in that case, you kind of building a theory around neural network, and you're establishing a first bound, like lower upper bounds on the number of bits that neural network needs, and then it might be improved in future by using next approach. But so like for now, like there is no other approach to do that, and that's why I feel it's important to say that it's actually related to neural networks, because there was no other comparable method right now. for this task.
Okay, thank you. Thank you.
Okay. Any other questions?
Okay, yeah, thanks for the nice talk. Yeah, first I just want to make this remark, just following what Vladimir said about compositions of functions. Basically, neural networks are compositions of functions, so it's there's not much
Yes,
difference.
yes, I agree. I agree.
Okay, so a couple of questions actually. So one of them, this is what you have just mentioned about the precision and the information content of the network. So usually there is actually kind of two scenarios. So the one scenario is in some of the constructions that you describe, you don't really need a lot of you don't really need a huge precision for the weights and the objects that appear in this computation. But this is not always so. So there are some pathological constructions with neural networks and ReLU functions where you can actually kind of achieve more. You can reach better complexity versus accuracy trade-off if you allow yourself to use more precision, some higher precision, very high precision. But this is not usually the case. So you started from the examples of the constructions for the approximation of smooth function, sine function, and so on. They don't really seem high precision. So the precision basically grows logarithmically with the size of the network and maybe with epsilon. So I'm not quite sure about the analytic functions and in the sine function, but I think that this is actually the kind of more or less natural the dependence of the information content of a single weight is more or less kind of reasonable. So it does not really scale too much with the size of the network or with the accuracy that you want to achieve. So you mentioned just in the very end that there is some other research where you can you maybe say just a couple of words about it? So do you what exactly do you show? Do you is there some kind of main idea that you can briefly describe about the information?
Yeah. So this all results can be extended to quantized networks. So if you quantize the weights, you can actually claim that I need that many bits in order to get that the given approximation error. So like what is tricky for this sort is kind of related to the histogram distribution, because when you are not precise so if you're not precise in the locations of the breakpoints in this inverse CDF, so basically when you quantize, like you basically changing the angle a little bit, making error here, and you also shifting this breakpoint like on the either on the horizontal or vertical line, and that screws up the histogram distribution. But that can be dealt with. And what the main thing we did was information theory is that we quantize a network. We computed the number of bits one requires for the ReLU network to have in order to transport one-dimensional uniform to arbitrary high-dimensional. And we actually shown that for histogram distributions, the number of bits is like very close to the optimality. So we obtained that in order to encode a network that approximates like this histogram distribution, one needs of log power of d inverse of error bits, while the fundamental lower bound is of log of epsilon of inverse and the error. So basically, instead of logarithm of epsilon inverse, we are having for histogram distributions, logarithm power of d of epsilon minus 1. That's a result we obtained. And we also have it for arbitrary distributions, but that one is not so close to optimality. For arbitrary distributions, we're getting something like epsilon to the power of minus d multiplied by logarithm squared of inverse of the error.
Okay, yeah, that was actually also my second question. I wanted to ask about lower bounds. So you basically describe upper bounds, right? So you can actually achieve the approximation using some amount of resources, and for some problems, for those that you mentioned in the beginning. Actually, also I'm not really sure about. I don't remember about the sine function, the periodic function. But in the case of the Sobolev functions, there is a kind of standard theory which actually gives you the lower bound for the required complexity of the network to do the approximation with given accuracy. So in this case, also it's a kind of natural question, and what it looks from your description, it looks that it may be related even not to the not to this piecewise linear approximation, but it might also be related to this histogram approximation that you're doing. So can you also maybe say something about it, about the lower bounds?
So unfortunately, we cannot find any research on the, so like what was nice about the normal neural networks approximations of Sobolev functions and like this cosine. We also have a paper on Gabor frames, affine systems. So there is actually existing lower bounds developed by like theoretically, for example, like they shown that wavelets are optimal for affine systems, or like Gabor frames are optimal for Gabor function classes. So basically, there it was established theory. What we have a problem with in this case with distributions, that we didn't find any information theoretical results on classes of distributions. Nobody talked, like at least I didn't find any results on classes of distributions. Everybody just like saying results on like general just distributions. And what I would say from our work, we developed actually a class of distributions, which is the histogram distributions. They have quite the histogram distribution. We can say that it's a kind of a class of distributions, and I'm pretty sure that we are optimal for the histogram, like close to optimal for the histogram distribution, because if we go to that problem from this bit length, like rate distortion theory point of view, we are very close to the optimality. So, but every time we are switching to like bits, we might lose something, and that's why. Okay, so like the answer to the question is that we cannot compare with lower bounds. We didn't like establish them because we didn't find research on the function classes for like for distribution classes. That we didn't find, and we struggle to develop them ourselves. Yeah.
Mm-hmm. Okay. Okay. Thank you.
Thank you.
So, colleagues, any other questions? So I think if no, so then I would like to thank Mintero. So thank you very much. So for very nice and interesting talk. Okay, so I think next time there will be a talk by Daniil Tepkin about some optimal transport questions. So see you next week.
Yeah, thank you very much for the attention.
So thank you very much for the talk. Yeah. Thank you.
Алексей, можете на минуту задержаться?